observation error and background error matrix, and we assume that to be Gaussian. There is one very simple reason for this, is that if you want efficient algorithms, Gaussian is your best guess. I mean, you can, if you have a quadratic function, you can have very, very efficient algorithms for minimizing it. That's what you need. I mean, you do experiments on a low-risk model, but I think even in your field, if you start to run with real size, if you try to take satellite observations, it is made of the sun, with some real-sized model to combine the two, you need to have some quick and practical algorithms, and you will end up using the Gaussian assumption in one way or another. But it's not such a limitation. For example, the background errors, your initial state, in some instances it is not Gaussian. For example, you can think about things with a bounded, like water vapor. It is bounded, it cannot be less than 0. And of course, when it comes up to saturation, it condenses to liquid water. So you're bound, let's say, between two physical limits. And of course, the PDFs become more or less skewed towards the two physical limits. And in these situations, what we do is that we make this a non-linear transformation of your background variable, which you want to describe statistics for, and then the statistics for the transformed variable are more or less Gaussian, even if the statistics for the original variable are not. That's how we deal with that. And and also for the observation cost function, we can deal with weak nonlinearities by changing the shape of the cost function solved for the Gaussian. But the important point here, which I wanted to make, is that we are looking for the maximum likelihood solution here. But in practice, you can see that sometimes maximum likelihood solution may not be the best one. If you have a very badly behaved PDF like this one, you might like the mean solution. But from my experience, and I think that if you talk with a statistician, you will see the same thing, and if you know your physics, you will see the same thing, that this is really a product of you not being too careful. You mix together two different states. For example, in meteorology, you might mix together cloudy and clear conditions with very different characteristics. So the trick when we see something like that is again try to stratify your error statistics, you're talking about errors now, according to some physical insight into how things would behave, how error would behave as a function of some physical parameters. And then you more or less get back to the Gaussian state. So what to say with this, we treat everything in Gaussian least square framework, which has very efficient algorithms available, which we need, but we cope with nonlinearities also by tricks like this. And we can do that because, well, we have a weakly nonlinear system, not extremely nonlinear. It's not guaranteed to succeed, but it does in practice. So, what we do now in practice is that we need to define what we have here, define the space over which we have this state variable and observation defined. And depending on a little bit how you do this thing, you can end up with different approaches. The simplest approach is like this. Let's see. Go back to our time dimension here. 0 to tau. We got some observations. Y1, Y2 is called Yn here. And we said we just want to have one analysis. Let's just map everything to one time instance, for example here. So we just find out which is so you just in time you just assume all observations are available at this time here, mix it together with the first case state here, and the observation operator then applied to x at this time compared with observation, even if observations are different time. So this is in a sense what we call 3D var. And if this time interval is small with respect to the major variation of your system, this is a very feasible approach and gives you very nice results in practice. The main thing here is that we got the variational framework still, we got the nice connection between observations, models with observation operator. But what we really want to do to improve upon this is to take into account the model evolution. And that is then what we call 4D bar. So three-dimensional variation data isolation. That is where you just assume all the observations in the time interval, appropriately chosen, to be valid at the same time. It's a very pragmatic first step. When I develop these algorithms, you always go to this first, because the real difficulty is developing the observation operators, minimizing algorithm. When you've got this in place, you can start playing, and then afterhand you can add in the model evolution.
Sorry, I'm a bit confused about this expression. Maybe I should have noticed it. X and Y doesn't have the same dimension.
Here,
right?
No, but h of x
has the same dimension as Y.
H of x, the same dimension
right.
as y.
So let's say X has dimension of 5.
Yes.
And Y has dimension of 3.
Yes.
Then left hand side is a column vector with 5 entries.
Yes.
The first term on the right hand side is also a column vector with 5 entries.
No, this is scalar.
All right.
Because it is.
Oh no, I'm sorry.
Yes.
I'm sorry.
There's no model in your equation.
Sorry?
There's no data M in your equation.
Not here. No, the M will come in here.
During time.
X. We get to that. I'll get to that in a moment.
Okay.
The model. This is just how we do the thing. But the model operator is hidden here. Okay, you've got the background. And how do you get to observation? Observation are valid at different times. You need to evolve your background to the observation time. How do you do that? You use a model. So this will actually be M of XP in here.
Excuse me, maybe I missed something. So why the dimension for X and Y different?
Because X is the dimension of the model. Y is a number of observations.
Oh, number.
Yes, of observations. So that's these are, so they don't need to have any relation to each other. They can be larger or smaller than each other, doesn't matter. Okay, so Sasha's question there, answer to that. Well, a slide after this. So we discretize this window into some time slots. That is the time step of our model. So we have xi here, which is a time step I, and in that we collect all the observations valid within this time slot and compare that with and calculate the observation operator for that as a function of the model. And the correlation, as I said, we assume that observation errors are uncorrelated. It's not a restriction. We found in practice that if the observation errors are correlated, you just increase the, you can show that you can increase the uncorrelated part a little bit and you will still be fine. And then the function on the previous page just becomes like this. We just discretized over the time steps of the model. The same thing, just I'm taking one step closer to the practical algorithm. And the next step is then to consider the model. Of course, xi here. Xi is m of xi minus 1. Of course, step one step to the next one. And what we're doing here in 4D bar actually is that we are finding an optimal solution subject to the constraint that a forecast or an integration starting from initial state follows the model here. So we're not adding any terms or changing any terms in the model. It's just change the initial conditions and then integrating model forward. You can, and that we call a strong constraint formulation, because every xi in this window has to fill this condition. We also have a weak constraint formulation, where we actually include the model error here. That's a very straightforward extension of this. But we have not included that in the presentation yet, but that's straightforward.
So the first part of the cost function, that may be on the previous page, is just operating on the initial conditions.
Yes.
And why is there no weighting factor between these two contributions?
This one and that one?
Yeah.
Because we assume that we are not talking in PDFs of the initial state. We assume that the initial state had nothing to do with how we observe things. The observations is independent of.
Yeah, but wouldn't it make a? I mean, you could put a larger weight on one of the two.
But the weight is in B.
You are saying that if I have evolved it for a long time, then maybe it has become independent of the initial condition, somewhat, so it should have a less weight, and that's what it means.
For example, yeah.
No,
This on external grounds should not necessarily always be the same.
But as an example.
Yeah. Yeah.
Like, are you not talking about successive times you will do this approach? Because B is just the error of your state of a particular instance.
Yes.
That can vary in time from one instance to another, of course. I'm not going into detail how I derive B here. I just assume B is given. You can derive that in different ways, more or less sophisticated. But the errors are given. We can discuss offline later how, very interesting, how do we actually derive these errors for our models?
Okay, so in the calculation of B, the calculation of B is not independent of the calculation of R.
It's completely independent.
It's independent.
Yeah, because observation of R, the calculation of R is something which depends on the observation system. That is just how is your radiometer measuring? What is the error of your thermometer? And that's pretty independent of your modeling assumptions, how you're integrating the model.
My understanding was that you want to minimize,
Yes.
maximize? Minimize the cost,
Yes.
yes. You want to minimize the discrepancy between model and observation. That's on the right-hand side.
Yes.
And you can do this by making additional changes in the initial condition, and that's described on the left-hand side.
Yes.
You could do that if it's not too costly.
No, but this is exactly if you are going to do what you described, this is exactly what you end up with.
Yeah,
Because
but then I don't understand why there's no weighting factor, some weight factor on the two contributions.
but there is a weighting factor. The weighting factor is P and R. These are the weighting factors.
That's why I was asking whether they are dependent or not.
They're not dependent on each other.
This is strange, I think.
Well, as I said,
It's like if you have a weighting factor P and Q, then of course Q is always 1 minus P.
okay, let's make a very simple example. We put a thermometer
They're
in.
independent.
See, that's only when you are, I mean, here you are not adding up probabilities. I mean, exponential of this is the actual probability.
Yeah, right.
This is a Hamiltonian, so to say.
Mhm.
So I think that's the sense of the law.
A very simple way to think about why this is uncorrelated is that if you got a thermometer here with a certain errors, we model observation error of that. If you or me make different models of the temperature in this room, the errors in our models are completely independent of the observation error modeling of the thermometer. That's how it works.
What's the difference between 3D and 4D?
Okay, 3D is the three space dimensions, take everything at the same time instance. 4D you take a time dimension into account, 4-dimensional. So that is meaning that you actually look at observations at the correct, you compare observations with model at the correct time.
But in 3D case, we can look for enough short time.
Yes.
period.
Yes, so actually, if there is a sequence of 3D, there is a slight downside in that you do things independently. If you do it over a larger frame, do everything together, then observations here can confirm observations there and can have influence on the state there, which you can't have if you are doing it sequentially, step by step.
But 3D meteorology is impossible in principle, right? Because the system evolves, you know, cannot really apply 3D meteorology.
You can, and we have. It's big, but you can't.
Unless it's hydrostatic or something.
No. No, you just choose the time period small enough, like 6 hours, which is a small enough time period for the major systems to be reasonably similar. So then the largest time discrepancy you have between your observed state, your state and observation is 3 hours on either side.
It's more a time derivative, right? No resolution, no model.
You see, you evolve your model, then compare the model with the observation at that time. That's a 3D var.
Update the model.
And then you go one more step and do another absorption. That's another 3D var.
Well, once you say evolve your model, it means you already have time dimension.
Yes,
Yeah, yeah.
you are not.
But 3D and 4D var does not refer to your model. It refers to the analysis, your data simulation. So it's 3-dimensional variational data assimilation, 4-dimensional variational data assimilation. Maybe the wording is not very good. It just refers to take into account the type evolution when you're comparing observations with models.
I take into account the previous states, right?
No, in the 4D you also take into account the future states.
You always collect observations over some time frame. And then how do you want to treat this? You have a model also evolving this time frame. So when you compare observation and model, 3D and 4D is just different ways of comparing observations with model. Either compare all of the observations with this one model instance with one time step, or you compare the observations in different time slots with the model in that time slot.
If I understood correctly, in 4D case we have time-dependent cost function. In 3D it is like
Why different times?
Yes.
Different times.
So if you wanted to predict the cycle solar cycle 24,
Yes.
based on cycle 23 alone, that would be 3D bar. If one took also into account cycle 22 and 21,
No.
it's 3D bar.
No. That's not quite so. Because even within a solar cycle, you don't just have one instance. It occurs varies in time. You have a model which takes into account. So the difference, if it's one solar cycle, you would just take all observations in that solar cycle, bunch them together, one instance, and say, okay, that is my mean. I don't know whatever variable you want to specify, solar sunspot number, whatever. That is the mean number. That is the one number. But in 4D, what you would take different parts of this and say, okay, that in this particular time instance, this year I observed so many, next year that many, and you would try to compare that with the evolution of the model for each year in that instance. That's the difference.
and also you should have enough data for analysis.
But I mean, if I didn't talk about cycle 22 and 21, but talked about 22.9 and 22.8, would you then agree? I mean, I'm not too sure why you said it wasn't right what I thought.
I think it is like this. So you want to make the prediction for cycle 24. And you say to do that, you will evolve your system from say cycle 23. Now the question is how you reach your state at cycle 23. Say you start from cycle 10 and evolve your model from 10 to 23. And in this whole window, you also have sunspot data. And in the whole window, you match them together. And that gives you the result at the end of 23. That's your 4D bar. Because you have minimized over sunspot data in one axis and time on the other axis. Now instead of doing that, you would have taken your model from say cycle 10, go to 11, then absorb the data from 10 to 11 to get the snapshot at 11, then go from 11 to 12, absorb the data again, and do it in this fashion till you reach 23. So that's like time evolution 3D bar, time evolution 3D bar. So that's the difference. See, in one case,
Yes,
in the 4D bar,
yes,
your cycle 20
yes.
will influence how your function actually looked at cycle 15, because we'll optimize it over the whole thing. Whereas in the time evolution 3D bar picture, your cycle 15 has no information about cycle 20. So these are two different kind of optimizations coming into play.
Yeah.
Right?
Exactly. And the feasibility of these optimizations depends on nonlinearity of the model. You cannot take it over a longer time period than.
The correlation time in the model.
Okay. I think that was more or less what we were describing here. Solar cycle versus doing everything together in one instance. Okay, so let's hit on with this. Okay, where is the? Is there a message? Okay.
It was from him.
Ah. So this is what we get now. This is the cost function as we say here. It's a function of the state x1 to xk, where each of these is just m of xk minus 1. And more has gone through this here. What we just discussed is four-dimensional analysis. And this trajectory, that is the integration that we have in this time frame, what we call trajectory. Integration from one. So, now, basically what you got now, if you want to go practically forward, is that you've got a very large scale minimization problem. And we got some dimensional problem about 300 million or something like that. So you need very efficient algorithms, and usually, let's say, derivative-free algorithms like just direct inversion of the 300 by 300 million matrix is not feasible to my knowledge. So we need to have some kind of iterative algorithms where you use graded information of the cost function to get to a proper minimum. And there are a couple of things that are important there. One is, of course, that you need to precondition a problem properly, because for all minimization algorithms, you've got some dimensions where you have very small errors, other dimensions with very large errors. You can end up in a situation like this where you have a very hard time to get the minimum. Whereas if you have, let's say, all dimensions of a problem have a similar magnitude, you just put that in this minimization cost function, you just put that spherical surfaces, and you have a very easy time of getting straight down to the minimum. It's just general knowledge from minimization. So,
on a quadratic function. So
yes.
minimize.
No, but you can multi-dimensional quadratic function.
You should gain the figures. Multi-dimension, but still it's quadratic, so it's just
yes.
minimum.
You need to minimize with respect to 300 million dimensions, for example. So if it is spherical, you can in one step get to the minimum. Whereas if you have 300 million dimensions, all are very, let's say, so you get a very oblong and function in no, yes, but with the direction of the gradient, it doesn't take it straight to the minimum. If you've got an oblong cost function, where is that? The direction of the gradient takes you there. It doesn't take you there. So
no, I mean, when you have a quadratic function,
yes,
the minimum is for the derivative is 0, right?
yes,
So, but you know, it's easy to differentiate quadratic function.
yes, it is.
So you have just linear equation to solve.
Exactly. Yeah. But if you, that is the point. If you want to solve that linear equation directly for 300 million variables, you have a very hard time. Unless you, Yeah, that's exactly. You use iterative techniques. That's what I'm saying. Because we always go to iterative techniques.
To solve the linear equations.
Yes. Yes.
Newton-Raphson or something like that. You mean Newton-Raphson? Or
Newton-Raphson is too slow. It doesn't work.
yes.
I mean, okay. So the first thing which I wanted to say, we can discuss that at some detail later. We need to do some preconditioning to make the problem good for the minimizer, any minimizer. You don't want to have some directions which are very small errors, all these are very large errors. So what we in principle do for all the variables in our models, we normalize them by the typical error magnitude. So all the errors are similar order magnitude in this transform coordinate. Then the cost function transforms to something like this. And this kind of transform limits the, let's say, the difference between the smallest and largest errors you have in the system, and that guarantees that you will have a reasonable convergence.
I mean, this the whole thing is so expensive because of this XP thing, not because of the h of x and y thing.
No, it's
That should be much less because the dimension is so much less normally.
yeah, and that is diagonal. Also, that is h of x minus y. That is diagonal, and you're very right. It is also expensive because of this b.
Yes.
Yeah.
So one could do some cross-graining.
That is what we do. There is no way you can take. We have like number of variables times the dimension. So we have like 5 times 300 million in 1 by 5 times 300 million matrix. We want to invert that. So what that is the description of B. So what we do is we make, let's say, on a multi-level some kind of a coarse graining block diagonal matrices. We take block diagonal matrices, a block within block within block. There are several levels of this. It's the only way you can solve this really. Hessian is the second derivative of your function, of the cost function.
The x I and by the x.
The state. Yes. So that describe the curvature of your function.
Oh, it's a matrix.
Yeah. Okay. Let's just so anyhow, to do this, I would recommend if you're going to do any kind of minimization, there are two very good algorithms which we can recommend, which are used by a lot of people in different fields. Both are available. This is available online, very robust algorithms. The Cauchy-Newton method, and in some cases, like in our case, we write our problem such that we will be solving linear problems. This also works with weakly nonlinear problems. So if you can write a problem so that it is linear, and I'll show you how to do that in a moment, we can use conical gradient method, and there are very efficient conical gradient methods.
Can you explain how we make, we choose the transformation method? Can you go to the previous slide because it's not clear.
Very.
How we find L?
Okay. Let's just take the. You were saying like 3 variable model, Lorentz model, whatever, with x, y, z, and the variance of those. I don't know what the exact values are. Let's just assume for fun that there is like 1 to 10. Okay, the variance of different variables. In the background, what we would write then, we would go, instead of using x, y, z, that would go to x divided by sigma x, y divided by sigma y, z divided by sigma z. That's all. That's the transformation, and then all of them have a variance of 1, these variables.
Which is normalization with respect to ours.
Yes. This is normalization.
So these are total of the time, right? So
sigmas, they are basically gradients of the initial condition.
Yeah. Variance, no, not the variance of initial condition. Variance of the error. Error.
Why there was this in the slide? Why do you want to normalize?
And that is because if you want to do minimization, such a function
Yeah.
is very difficult to minimize.
Yeah.
If you transform it like this, you get something like that,
Yeah.
it's easy. There's a difference between feasible and non-feasible.
That's in your second equation then. That's what you're doing.
Yes, exactly. This is a rewrite of the previous one. So these are very important concepts that you want the efficient algorithms, you want to precondition your problem. So we need to keep that in mind for practical algorithms. Now, let me just say that in practice we have nonlinear cost functions. So what we do instead, our problems are nonlinear. Let's say this blue line here, it can even look worse than this. So in practice, we know that we have a reasonably good initial condition so that we are in the neighborhood of our reality. So if the real reality is here somewhere, we start here, this is somewhere in the neighborhood. And then what we do, we linearize our cost function around this state, it gets something like that, solve this linear thing, get a new solution, calculate, and then we linearize around that solution, and we hope that the sequence of linearizing the nonlinear cost function, solving it as a linear cost function, and that sequence in time will lead you to the right minima. There is no guarantee it will do that, there is no proof that it will do that, but in practice, this is what we have found works.
The nonlinearity of the cost function
Yes.
has nothing to do with the nonlinearity of the equation, right?
It has a lot to do with the nonlinearity of equations, because in the cost function, you have the comparison between observations and model at the appropriate time,
So
where the model evolution comes in.
Yes, so nonlinearity of the cost function comes from the nonlinearity in H or
Both. It comes from the nonlinearity of your observation operator. For example, you could be measuring something which very sensitive, depends on parameters you don't know. And it comes from the nonlinearity of your model. Both. Because there are two terms that both can be nonlinear.
that's only in 4D one.
Yes. In 3D, it's only the nonlinearity of the observation.
But I mean, I still don't understand why they are dependent on each other. The model could be completely linear. The
Yes.
observation can be highly nonlinear.
Yes.
Yes.
And then, of course, it comes from the nonlinearity of the observation in that case.
Yes. But
So therefore, it's completely independent of how nonlinear the actual model was.
no. In 4D, no, because we are not talking about the nonlinearity of the observation error or the observation. We are talking about the nonlinearity of the observation operator. It's an operator acting on the model, function the model integration.
Whole thing, yeah.
Yes. Okay, so that's a little bit how we do this, and another thing is that the dimension of this problem is prohibitive. So what we try to do that in each of these linear problems, try to reduce the dimension so that we have some, let's say, we can write, let's say, when we iterate this, we have some guess, and we write the cost function in terms of the difference between the reality or the state we want to seek and this guess.
Excuse me, it's G, it is like a background.
Yes. Yes. This, these are these states. You do the first minimization around your first guess, solve that, get this, then xt becomes this, solve that, get that, and xt becomes that. There's a sequence of minima of a linear cost function which hopefully converges to your nonlinear global system. And we don't need to go through that exactly in detail, but the function which we had above. You can rewrite that for each, in this linear part, with respect to your xg, or with respect to your previous iteration. And I don't go through this slide in detail because that is just putting in variable substitution. So this is linked to a linear problem where we, let's say, we have as a starting point our nonlinear operators, but then we linearize all the operators, the model and the observation operators, just for the purpose of this single step. So I think it is getting on quite a lot. I don't know if we should go much further. If it's lunchtime.
Yeah, we can make a lunch break. Yeah, afternoon, right? Huh? We can just continue in the afternoon. Then we can clean up 4 o'clock. 4 o'clock. 4 o'clock. Yeah, what did you say? I'm just asking. I said 2 o'clock. At 2 o'clock. Yes. Let's make a lunch break and then continue at 2 o'clock. Yes.
I mean, the only thing which I really want to present is it's quite important. I probably need a break to go through that. It's just a very practical idea that when you're, okay, we got this here, how do we implement this in practice? And that brings us into the concept of these linear models, sequence of linear models, solving a sequence of linear models, and how we do that.
We can consider now minimization as a black box,
Yes.
Don't worry about it, but what's important to understand, principles what goes into this black box.
Yes.
And so the entire data assimilation thing, what is a good test example?
A good test example is, let's say, in your field, if you've got some, well, actually, it's good to have a range of models. Let's say, order of magnitude less than your real model and 2 orders of magnitude less than your real model. Like in metrology, what we might do for trivial, let's say, just for playing around, we might use a lowest model, it's a 3 variables. But then to really test some ideas for research in some more real framework, we might use simplified model, which may be just 1-level model instead of having all 3 dimensions, so 2-dimensional model, could be a shallow water model or something. Quasi-geostrophic model, very, very nice example.
Lawrence is good. So Lawrence is a good example, yeah?
Lawrence is good, but it's only a very, very, very first step.
Yeah,
to get any kind of, I mean, I would recommend against spending too much time on a Lawrence model because that leads to false conclusions. Because everything works in Lawrence model in terms of computation speed. Because when it comes to real algorithm, you want to do something, you have to think about efficient codes. If you don't have efficient codes, you're just painting yourself into the corner. That's nice to have 2-dimensional model. Where you have some features reasonably described, you have some observation of that. You can develop a lot in that framework and experiment within that framework. That's a very good test bed, I would say. Instead of going to a full 3D model to start with.
Yeah, all right. Yeah, I think still we should do Lawrence first. For illustration, maybe control count.
We have developed with Lauren a very simple alpha omega Cartesian dynamo using the adjoint method with Olivier-Talagrand. So we have a simple step. We come here to actually finish a paper to submit it. So we went through all this process of doing the variational method, writing the adjoint code and all that stuff. And you learn from your mistake in this procedure, I think. You start with concept, you have equation, and then you have to actually make an adjoint code. You learn from it. It's not so easy to invert a code.
You actually never talked about an adjoint code.
It's coming.
I haven't come there yet.
What?
I haven't come there yet. That's what I want to talk about.
Yeah, because to actually evaluate the gradient of the cost function, it's better to do the adjoint code and to go backward in time. So you use your forward code to go forward in time,
Yes.
then you use your adjoint code to go backward in time, and by doing that back and forth, it's much easier to minimize your function and to compute the gradient of J.
Yeah, because this backward-forward integration gives you the sensitivity, or it gives you the full gradient, the full state of gradient. Whereas otherwise you would have to perturb with respect to each state variable, and that would be infeasibly slow.
So backward integration of time in time, not of the actual equation, of the
Of the adjoint.
equation.
And that's very interesting.
Yes, and so that, does that, for example, mean negative diffusivity and stuff, or what?
No, diffusivity, adjoint operator diffusivity is diffusive.
Is divisibility. But that's
Maybe
something you
negative.
can go
No.
through. Yeah.
Well,
I mean,
no,
diffusively speaking, if you go backwards in time.
no, the minus sign comes in terms of the time derivative. That's where the minus sign comes.
Yeah.
But the diffusivity operator is still positive. It's just a marginal dimension of time which is negative. Actually, what did you have that?
If you just write down the Burger's equation, u by dt, yeah?
Yeah.
Then you have minus u right squared u, or minus u prime, and you have plus u double prime.
Yeah.
So now you go backwards in time, then the diffusion operator goes up, right? Of course.
I guess you have a very systematic procedure to determine the adjoint, and this is you apply this procedure and you find all the expressions and you have your adjoint equation.
Yes, so how does it look like with the Burger's equation?
I can show it. I mean, it's not too difficult to do on the blackboard. We can do it. I guess.
Yeah, well, that's what we did.
It's what we did.
But it's true that you change the sign of the d by dt,
Yes.
but you don't change the sign of the diffusion.
No.
And the advection operator?
Advection, it's a strange one. Yeah.
Right, but
It
everything else
changes from-
changes except diffusion, and you could just say nothing changes and you only change the diffusion, which is what I thought.
I think there is also
Which makes sense, I think.
there is also another term which makes the equation non-homogeneous on the right hand side, which comes from your observations, etc. So
That's very, very interesting.
see what you mean. See, the adjoint depends also on the observations. You are taking that into account, right?
Initial condition or what? No.
Initial condition also observations on the way.
Mhm.
So they will come on the right hand side. I think it will become homogeneous, right?
Yes, it will be like a forcing term in your adjoint equation, the observation.
So they will come the forcing term in your equation, which will probably not allow you to draw. As we want it.
Yeah, but probably so, but
Yeah.
Well, I mean, the adjoint code is just here to calculate the gradient of the cost function.
I mean,
So
you can derive the adjoint also. Related, I mean, I'm not done that yet, but if you can do it in nonlinear framework, is what you do is we had this, but we had at the start. We had the model observations and initial conditions all had their errors, and just wrote down the whole function of including all these terms, and do the minimization just with variational analysis, and out pop in the end this adjoint equation, and that is just systematic integration by parts, and it pops up in the end. And but it's not very useful framework, even if you can do that. It doesn't teach you how to do things in practice.
See, if you take J as the Lagrangian, then that's basically the Euler Lagrange equation.
Exactly. So Euler Lagrange equation of the forward equations.
That's the thing we were writing in the cost function will actually act like a Hamiltonian level problem, navigation problem.
but why do we need to deviate backwards in time?
No, so when you then when you minimize that cost function, you get see there. Okay, let me put it this way. Assume that the function you are trying to minimize, you know it as a function of x and t.
Yes.
then there is no problem. But you know these functions only as a solution of a differential equation.
Yes.
So in a sense, something like some differential operator L acting on x equals to 0 goes into the exponential of your functional integral. You see what I mean? If you try to do a field theory of stochastic PDEs, you have the same kind of problem, right? It's like if you try to do a field theory of Navier-Stokes. You basically have the same kind of operator lying on the top, right? Makes sense, right? And then you try to write the Euler Lagrange of that. So you will not only have the original equation you put in, but you will also have another equation corresponding to the adjoint variable. And that will be an equation which is going backward in time, but will have force things which depends on your observation. So I think you have to actually do it for a simple system, and only then you will have the right intuition.
So the business about this diffusion changing sign, this is really only a... everything else changes in time then. Yes, that's just a trick, because, isn't it? Because the whole formalism doesn't really work for dissipative systems, precisely. Is that?
I mean, of course, for dissipative system, the dependence of initial conditions will dissipate quicker. So you need to do this one more period, otherwise you will be. So it's, let's say, it doesn't make sense. If you have a very dissipative system and you make too large a time frame, because not predictable you can start, and it's not really good. You need to reduce it time to get to the sensible scale.
Axel, what is the question? Why, if you change
I mean, does it,
time direction,
yeah,
you will change the
in
sign?
other words, is it a rigorous procedure in it for a diffusive system? Or is it just an approximation to deal with, to be able to deal with diffusive systems?
Well, this is the same like if you write Lagrangian trajectory
Yes.
or Venus trajectory.
Yes.
And just write Venus trajectory. If time goes in the inverse direction, you write here plus some Venus processes. If time goes in the right direction, here there will be sign plus, and that's it. So it means that you have here, this point, and so this is x, and this is sign. Just to change the sign here. That's it. The same situation.
But you cannot really go backwards in time, right?
No, you can go back in
Yeah,
time.
but you don't get back where you came from.
But it's a different variable.
Okay.
It's not the same thing.
So this is point x t. Yeah, so you
Okay.
this situation when you go back in time and this plus you have situation and you go continue. But of course diffusion operator doesn't change the sign in this case.
I think the worry is that instead of taking one particle,
Yeah.
if you take a cloud of particles, which were very concentrated at 0,
Yeah.
they will spread, right?
Yeah.
But then when I go backward in time, they will all come back to the same point. That's
Yes,
what you
yes,
want.
exactly, exactly. Yeah. Yes.
That's what is your
In
motive.
that case, in any case,
Yeah,
diffusion
you don't
operator
get that.
doesn't change the sign.
You don't get what? Sorry, what?
In any case, diffusion operator cannot change the sign. If it goes back in the time or forward in the time. Just to change sign before Lagrangian.
So what happens to the cloud? It really becomes smaller.
If there is no observation, if there is no diffusion, it becomes smaller. But if there is diffusion, it is still possibility of
Yeah, of course.
growing.
Backward in time.
Yes.
Yeah, of course.
Yes.
Because each step to the forward
Yeah,
depends
yeah.
on
Yeah.
the neighboring point.
Yeah, of course diffusion causes that you have
Mhm.
in both trajectories. Yeah, in both direction, yeah, of course. Yeah.
Wij spreken toch wel